My name is Juan Suarez, and this is Physics 1 Video Lab 3. In this physics lab, we will simulate the motion of a spaceship to determine its initial velocity. And the purpose of this lab is to apply principles of gravitational interactions, Newton's law, and simulation techniques to analyze the motion of a star that's orbiting a black hole and estimate the black hole's mass and initial velocity. When we talk about Newton's second law, we must talk about the formulas above, which is F net equals dP over dt, which is a simple way of saying F equals ma, where A in the term of this lab is a gravitational force known by Newton, which would be F equals mg. Parallel forces act in the same direction, which aid acceleration when aligned, and perpendicular forces act at right angles, which induce rotation and torque and angular motion. Using these two, we get circular motion velocity, which is mv squared over r. Universal gravitation states that every point mass in the universe is attracted to every other point mass, which we can use the formula above, where F is a gravitational force, G is a gravitational constant, M1, M2 are the masses provided, and R is the separation distance. Free body diagrams are visual representations used to analyze physics and analyze the forces acting on an object. For example, the one we see on the right, we can see the gravitational force of the Earth and the centrifugal force and the force of the acceleration in comparison to the sun. The previous questions for this lab include, can you find the mass, how will the forces look like, how will the code look like, and does the coding give evidence to the experiment? To answer these questions, we can find the mass using the first version of the experiment. The forces will look like F net, F perp, and gravity, where one arrow points in the direction center of the rotation and the other one with the acceleration. The code will look slightly similar in both with a change in the velocity. And does the coding give evidence for the experiment, which it does in the what if and other questions stated later. The systems and surroundings are as follows. The systems are the star, the black hole, which is both a system and a surrounding, and the spaceship. And for surroundings, we have air resistance, gravity, external factors, and space. The initial conditions for most of the experiment are to the left, where the gravitational constant is 6.7 e to the negative 11, the mass of the star is 2 e to the 30, and then the time that we allocated was 24 times 60 times 60. All you need for this lab is the starter code. This experiment has 3 parts. Setting up the star trajectory, which you will use the provided starter code and an email address that is yours only with a unique star trajectory. Second, you will find the mass of the black hole by analyzing the star motion to find the net force, assuming that the net force is only on the black hole at the origin, which you can then use to find the mass of the black hole. And then the spaceship motion simulation, you will use the second starter code provided and enter the estimated mass found before and determine an initial velocity so it can leave orbit. Version 1 of the code contains multiple different formulas including F perp, F parallel, and the universal gravitation. The code above will simulate a star orbiting a black hole, and using the dynamics that generate the star's elliptical trajectory, Newton's laws will calculate the gravitational forces. The trajectory customization adds a touch of randomness depending on what email you have. These forces are decomposed into parallel and perpendicular components, shedding light to the intricate interplay of motion and gravity. Arrows visually depict these forces, offering a hands-on exploration of these mechanics. What we concluded was that the net force was 9.59 times e to the 28. The parallel force is 3.43 times e to the 28. The perpendicular force is 8.94 times e to the 28. And the mass, which is the average of all the data points required, was 1.27 times e to the 34. This glow script code simulates a spaceship and a planet orbiting a black hole. The gravitational forces between the black hole, planet, and spaceship are calculated in the code, and their movements are updated using Newton's law. The simulation incorporates conditions to avoid crashes, such as getting too close to the black hole and colliding with the planet. The trajectories that we calculate further provide insights to how the black hole affects the spaceship, and we can see further the ship speeds that we chose and the different forces that we can act on, such as F ship, F net, which are highlighted below. The results that we concluded was that the initial velocity is a negative 3.1 times e to the 7 in the x coordinate and 5.3 times e to the 6 in the y coordinate, with a distance from orbit of 3.40 times e to the 11th power. Because of the nature of this lab, you can only have 2 types of errors, rounding values and simplification of formulas, where a formula does not encapsulate the whole essence of the situation. How does the net force and its parallel and perpendicular components differ from the rate of change of momentum and its parallel and perpendicular components? In short, the net force is a vector sum of external forces that influences the object's acceleration and motion, while the rate of change of momentum signifies the momentum over time, which gives more examples and responses to the external forces that are acting on the object. What if we wanted to make it an orbit and not fly out of orbit? What initial velocity would we need? So in the context of this experiment, we determined this numerical value with intricate calculations such as determining the gravitational forces that are exerted by the black hole and the planet, and it requires finding some equilibrium. I changed a couple of numbers, as you can see on the top left, and you can see the picture that I got in the middle, which had one big orbit and the small orbit, which is perfectly circular, and the velocity I got was negative 2.0 e to the 6th and 0.75 e to the 7th, which you can get using universal gravitation formulas and the F-perp and F-parallel formulas. In conclusion, this lab provided a comprehensive exploration of gravitational interactions, and we successfully estimated the mass of the black hole, leveraging the principles of Newtonian physics and gravitational forces.